Generally, structural attributes are used to measure either similarity or dissimilarity between neighbouring traces. They use differing methods to achieve this and are data dependent. They can give great results if you understand what the input parameters mean. In this series, we will review the structural attributes available in DugInsight and look at some examples. In this video, we're going to look at two common structural attributes used in fault identification and explore their input parameters. Let's get started. Here I have an Insight session showing some clear faulting in the section view. The upper left map view shows a slice through the same volume at 900 milliseconds, marked by the blue line in section view. Faulting is seen in the slice view, but not as clearly as in the section. The upper right map shows a pink horizon visible in the section. The faulting is clear in this map view, identified by a rapid change in colour. Incoherence and correlation similarity both use the same correlation calculation, but in different ways. Incoherency measures dissimilarity between neighbouring traces, whereas correlation measures similarity. They also use a slightly different weighting method to calculate the final volume. Both are very useful when exploring a dataset for faults or channel features. I can create an incoherence volume in the Process tab, create a new process, select Incoherence from the list, and then type your own name, or accept the default name. Add the input volume. Since this process will highlight dissimilarity between the most similar neighbouring trace, I should bear in mind any dip noise in the input volume that may affect the final output. For particularly noisy data, you could first apply a structurally oriented filter and feed this as an input into the incoherency process. It's important to define the calculation window. For incoherence, Insight will calculate the correlation for a range of dips within the window, at each sample between the current trace and the next trace. For 2D volumes, this is pretty straightforward. However, for 3D volumes, Insight will apply the calculation independently in the inline and crossline directions. For 3D volumes, the option Output Statistic will determine what happens during the calculation, whether Insight uses minimum, maximum, or average statistics to achieve the final volume. The trace half window should be large enough to encompass the entire feature you are trying to resolve. Too small, and the output will be noisy. Too large, and it will not resolve the feature. For this example, I'll use the measuring tool to measure the largest feature I would like to resolve. In this case, the smaller fault throws are between 20 to 30 milliseconds, and the larger throws are approximately 140 milliseconds. And so our trace half window should be 70 milliseconds. The maximum dip tells Insight the dip allowed before reporting as a dissimilar or incoherent event. I can do a quick calculation based on the general dip of our horizon by using the measuring tool and calculating the gradient of a line. In this case, the change in vertical, 70 milliseconds, divided by the change in horizontal, 1000 meters, gives a dip of 0.07. Let's round this value to a parameter setting of 0.1. Now to see our results. Areas of maximum dissimilarity are given a value of 1, and identical traces based on our inputs return a value of 0. I'm seeing a nice fault network appearing from this horizon. Let's compare this with correlation similarity. Correlation similarity uses an analysis window to measure similarity of neighbouring traces. The input parameters are very similar to incoherence, but the background calculations are a bit different. Incoherence calculates the difference between the most similar neighbouring trace, whereas correlation similarity uses an analysis window of one middle trace and its 8 neighbours, then averages the results. This can lead to this attribute running a little slower than incoherence. I can create a correlation volume in the Process tab. Create a new process, select correlation from the list, and then type your own name or accept the default name. The half window vertical distance and maximum dip parameters are calculated the same way, as specified for incoherence earlier, so I'll use the same values. Note that the bigger the maximum dip, the the longer the processing time. I can make adjustments to the input parameters at any time, as these attributes are calculated on the fly. For a direct comparison to incoherence, the reverse output option is ticked on by default. When reversed, high similarity values will have a value closer to 0, while low similarity values will be closer to 1. I can use Doug Insight's group functionality to overlay these structural attributes to help guide my interpretation. After creating a new group, I add 3 volumes and assign the 2 structural attributes to the top of the list and the stacked volume to the bottom. Selecting the group in the map view displays the combination of the volumes, but it is only by setting the attribute classes to a transparent color bar that I clearly see the combined results in both map view and section views. Using the hide and show toggles in the groups, I can see incoherence or correlation or both volumes overlaid on the stack data. After choosing the best display, the fault segments can easily be picked in any of the views, using the structural attributes as a guide. Watch the rest of the video series to learn more about structural attributes.
If you have questions or would like to discover more, then visit our website at www.doug.com. And remember, have fun with Insight.